Hey, folks, hope you're doing well. Today, I just want to take a little time and I want to kind of go a speed version on through the main points of this unit and some of the key components so to make sure that we're all ready to be successful next week. Just a couple items. Tuesday, again, as I mentioned, I will not be in school, so you'll have a sub. There will be a video lesson that day, a little review. On Tuesday, it will focus more on kind of the balancing of equations and in the STEM classes, some of the mold problem type problem solving questions. So that's what to be looking for. And also there will be a second quick quiz then that will be added or a second practice test, if you will, be added on Tuesday that the sub will be given to you. And that will be available, and hopefully we'll all be squared away and ready to do a great job on Wednesday when the test comes. I will say again, if there are things that you have questions on, please be sure to come prepared on Wednesday at the beginning of class to ask those so we can address that, and then we'll get the test done and we'll be on our way. Well, I do want to as I mentioned, I want to kind of go pretty quickly through this unit and just make sure that we are understanding the key components. Again, when we talk about chemical reactions, we're talking about changing from one substance to another. And in that process, we have chemical bonds that get broken and new ones get formed. Last unit, of course, we talked about different types of chemical bonds. We learned that it's the electrons that are kind of the players in the game that do the rearranging and do the actual chemical bonding. And in order for a chemical reaction to happen, they have to physically come in contact with each other. And another key premise about chemical reactions this unit was that the law of conservation of mass gets observed, that we don't create or destroy matter. And so when we start a chemical reaction, we have, of course, our beginning materials or starting substances. Those are called the reactants. When the reaction runs, we end up with something new. Those are going to be called the products. And the arrow between the reactants and products, of course, is meant to mean that it produces or yields or forms in a chemical reaction. Not quite like an equal sign like you might use in a math equation. In a chemical equation, of course, we put that arrow in there. Reactions tend to follow certain patterns, and there were a few different varieties, of course, that we looked at: synthesis, decomposition, single and double replacement, and combustion reactions. We talked about how in a synthesis reaction, we put a couple things together, two elements together. Much like we use the analogy of Brad Pitt and Jennifer Aniston, when that happy couple found each other and fell in love, of course, they became a compound. They became a couple. And we did a little demonstration with that, and we'll just replicate that here really quickly. If you recall, we reacted a little magnesium with oxygen. And this reaction is a little tricky because while we see the magnesium and the magnesium ribbon, the oxygen seems to not be present. But of course, the oxygen that we're talking about is present in the air around us. And so in that way, I can drop my piece of magnesium. Sorry about that. If I bring my lighter up here to the magnesium strip, one of the things that we know about in chemical reactions, sometimes it takes a little bit of energy in order for the reaction to get going. And then once it gets going, we get this bright white flame being produced as the magnesium and the oxygen combine to form that compound, magnesium oxide. In the end, we get this flaky, flimsy material here of magnesium oxide in the reaction, and we've got our new product. Now, the next type of reaction that we talked about, of course, was a decomposition reaction. And that's where we would break a compound apart. And we would break it apart much again like the poor story of Brad and Jen, where we had a compound and you get the new distinct elements. Well, we did a lab in here where we saw that as well. Okay, we did a lab with the elephant toothpaste. If you remember, we had some hydrogen peroxide, and the hydrogen peroxide you put into a flask. You guys use this little smaller flask than this, but I'll just pour a little bit in here. And then hydrogen peroxide just on its own will decompose into water and oxygen gas, but it goes really slow. Now I'm going to put a little bit of dish soap in here because that'll help us see the reaction better. Mix it around a bit. But if you recall, the reaction could happen quite vigorously and fast if we added a little catalyst to the mix. Okay, the catalyst we used was potassium iodide. And when I pour a little potassium iodide in, it's going to speed up that decomposition reaction. And we get the foaming mass coming out of there. So again, it's all about the energy involved as we learned about how a catalyst works. All right. Energy involved is going to be cut down when a catalyst gets added. And so we get this nice little bubbling mass going. Well, we'll let that drain out in the background here. Our next type of reaction was a single replacement reaction. Okay, oh, again, in synthesis and decompositions, of course, were just the reverse of one another. But in a single replacement reaction, of course, we have a third element in the equation. We got a compound and an individual element. Enter Angelina Jolie as she replaced poor Jennifer Aniston in the process and left Jen off on her own. So one element was replaced, a single replacement reaction. Okay, again, single replacement can look different if, depending on element C, because sometimes element C might take the place of element A in the equation. All right, and in that case, poor Brad would be left off on its own, and that depends on if C tends to want to react with the negative compound instead of the positive compound in a chemical reaction. In a double replacement reaction, now we got two compounds, AB plus CD, and essentially what happens, of course, is those couples swap partners, basically. Okay, and A goes with D, C goes with B, and we've got our new compounds. Then we learned about a combustion reaction where we burned a hydrocarbon, and that can look a number of different ways. Lots of different hydrocarbons out there, but hydrocarbons are organic compounds made mostly of carbon and hydrogen. Some have other things mixed in the equation as well, like ethanol, which of course we did a little demonstration with. But every time I burn a hydrocarbon, all right, I'm going to react it with oxygen. Anytime something burns, it's going to react with oxygen. And I always make carbon dioxide and water. And so the oxygen is going to kind of split up and one atom of oxygen goes with the carbon, one goes with the hydrogen, and I get my new compounds. The demonstration we did for that, of course, was our milk jug, and where I took a little ethanol and just needed, if you recall, just needed about 10 milliliters of it. And I put that ethanol into a milk jug. And I shook it around. And the idea for that is I want those reactants, in this case, the ethanol and the oxygen, to interact well. And if I can, aerate them, okay, I'll be able to get them to react together faster. Now I'll just clear out a couple of things out of the way, and we can do this one more time for you. Oh, I left my lighter over here. Again, the more I can get evaporated, the better. Get this ready. I'm ready. Nice little combustion reaction in the process. So we saw some good demos of those, and hopefully we can see where they apply in terms of some different type of forms of chemical reactions. Another thing that we focused on then, of course, was the law of conservation of mass. So we don't create or destroy matter in a chemical reaction. We can blow it up like we did with just the combustion reaction there, but the atoms that are involved are still there. Okay, they're still in there. Same atoms and the same quantity. We don't get to create or destroy matter. The same things that are in the reactants have to be in the products. Now they're going to rearrange what they're chemically bonded to and form new substances, but they're made of the same things. And then we got into balancing the equations, and we talked about how we can use coefficients to do that. And the coefficients always have to be positive whole numbers. And so we get the same number of atoms of each element and the reactances and the products. Where there are no coefficients written, of course, those are ones, but we don't write those, and they're just going to be assumed. And then we have, if we have a coefficient in front, it's going to apply to all the elements in that whole formula. We talked about chemical energy, about the energy stored in the reactants versus the products. And when we talk about chemical energy, it's stored in the chemical bonds. And in some reactions, there's more energy in the products than the reactants, or in the chemical bonds of the products versus the reactants. And so you have to add energy to it. Like when we gotta bake our cookies. All right, you got to keep them in the oven. They have to draw that energy from the oven around it, their surroundings. In exothermic reactions, like we just saw demonstrated here, there's more energy in the bonds of the reactants than the products. And so then once I get that reaction going, it kind of runs downhill and it takes care of itself. All right. You'll notice again that little bump in each of those graphs represents that activation energy. They need a little bit of spark, and need something to break the initial bonds of the reactants to get the reaction started. Now I can increase or decrease my reaction rate based on a few different factors. Okay, depending, it could be, I can increase my temperature or lower my temperature depending what I'm trying to do. Okay, I can increase or decrease my surface area. Okay, limit or increase the amount of space that the compounds or elements have to react in. Okay, I did that with a little mortar and pestle when we did the one demonstration with the potassium permanganate. We can stir it just so those different elements come in contact with one another. Okay, and I can increase or decrease the concentration or the number of particles of the substance in a space, so that will either increase or decrease how often they interact and can react, or whether it's a concentrated mixture or a diluted mixture. And then, like I just did with the demonstration in the hydrogen peroxide or the elephant toothpaste, I can add a catalyst, and that's going to speed up a reaction that and it doesn't get consumed. Okay, oops. Inhibitors slow down those chemical reactions. We learned a little bit about acids and bases. They form hydrogen ions. In solution, acids do and are corrosive. They taste sour, have a pH less than 7. And usually their formulas are going to start with an H at the beginning. The hydroxide ions get formed by bases. And bases tend to be corrosive and taste bitter like soap. Okay. And they're going to have a pH between 7 and 14. And when we look at a lot of their formulas, they end in OH, or that hydroxide ion, as you might imagine, because that's the kind of ion they form in solution. And that pH scale goes from 0 to 14. The lower the number, the more acidic it is, which is can be counterintuitive sometimes, but the higher the number, the more basic it is. Right in the middle at 7, like pure water, is going to be neutral. And we can kind of tell that. We did that in the lab with the pH paper and used an indicator to help identify whether something was an acid or base, and specifically what the pH of those materials were based on the colored codes that happen, because indicators will change color accordingly. And then when I mix an acid and a base together, we learned that a neutralization reaction will occur. The hydrogen ion and hydroxide ions combine and they make water. And then the other two elements in the equation, sodium, in this case, sodium and chlorine, combine to make salt. We make salt water. And again, salt can be kind of a generic term. It can be, it's not always, it's, table salt like this one is. All right, but that's the last item that that I neglected to mention also was equilibrium again, and that's when reactions go in both directions. And they're going back and forth, and that arrow isn't just going in one certain way. It also is going back the other direction, as the products could sometimes turn back into the reactants. All right, I think that pretty well wraps up, in a nutshell, the things that we covered this unit conceptually. Like I said, on Tuesday we'll have more with the problem solving and the balancing equations, etc. Give you a little more practice with that and go over some of that. Have a great weekend, and thanks for tuning in.